In this video, we're going to learn how to predict the precipitates in a double replacement reaction. The first thing I'm going to teach you is that if you mix two solutions, it doesn't necessarily result in a double replacement or any type of chemical reaction. So for example, if you made salt water at home and you took bath salts or Epsom salt and dissolved that in water, and then you mix those two solutions, you would see absolutely nothing occur. And that's because the two potential products, sodium sulfate and magnesium chloride, are themselves soluble as well. And so you would just end up with a solution of sodium ions, chloride ions, magnesium ions, and sulfate ions, and you would see absolutely nothing, no change. On the other hand, if you were to mix potassium iodide solution and lead 2 nitrate solution, you would get a reaction, and it looks like this. Now, how do I know that this is lead 2 iodide, that is this yellow stuff that's precipitating out as a solid and sinking to the bottom? How do I know that it's lead 2 iodide and not the potassium nitrate? Well, here's how I know. I can go to this chart right here, and I can find that if I combine lead 2 ions with iodide ions, their compound, being shaded in, is insoluble. On the other hand, the other product of this reaction is supposedly potassium nitrate, but if I look at their combination, I see that as being soluble. So as I'm writing my products, you switch the potassium and the lead, you end up with the lead being with the iodide, the potassium with the nitrate. I see that it's the lead 2 iodide that is the precipitate, whereas the potassium and nitrate ions remain aqueous. Now, you could always refer to this table here, but just some guidelines on solubility. Guideline number 1, any group 1 ion, meaning lithium ions, meaning sodium ions, meaning potassium ions, any of those group 1 ions, or ammonium ions, nitrate ions, chlorate, perchlorate, or acetate, any compounds involving those ions are soluble with absolutely no exceptions. Another guideline is that if the product of the charges and ions in a compound is greater than or equal to 4, the compound is probably going to be insoluble. So for example, aluminum phosphate, well, aluminum is +3, phosphate is -3, 3 times 3 is 9, and yes, I'm taking an absolute value. That product of 9 is greater than 4, so this is going to be an insoluble compound. And what we can say is that we can relate it to Coulomb's law and Coulombic attraction and lattice energy. We know that the aluminum and phosphate ions, because they're so strongly charged, think of like two really powerful magnets stuck together. They're not going to be easily pulled apart and separated to form these dissociated aqueous ions. On the other hand, copper 1 sulfate, well, the sulfate is -2, and each copper, because there's 2 of them, each copper is +1. I take the 1 and the 2 and I multiply them, I get 2. This is less than 4, so we have a soluble compound as copper 1 sulfate. Now, there are some exceptions to this rule or this guideline of the product of the ion charges, and they're the following. Silver compounds and hydroxide compounds tend to be insoluble. The exceptions are anything up here. So silver nitrate, silver chlorate, right? Ammonium hydroxide, lithium hydroxide, those would be soluble, but pretty much any other silver compounds or hydroxide compounds will be insoluble. And the other guideline I have is that sulfates tend to be soluble. Magnesium sulfate, copper 2 sulfate, zinc sulfate. Actually, if we go to sulfate here, we can see lots of soluble compounds with a few exceptions being insoluble. Anyway, those are my guidelines on solubility. Hope this video has helped. Feel free to leave any questions or comments in the comment section below. Thanks for watching.